So it's a pleasure to introduce today and host here Dr. Jian Li. He is nowadays in EPFL, but the work that he will be presenting, I guess, you can correct me, was done in Université Paris-Saclay with Professor Gazal. So it's a pleasure to have you here, and now the floor is yours. Thank you very much.
Okay. So thanks, Jordi, and choose the invitation. And I'm very happy to be here to deliver a presentation. And today I will report graphene-based materials for energy conversion. First, we will give a brief introduction of the graphene. We can see this graphene. This graphene is different from graphene because graphene only consists of sp2 carbon atoms. But for graphene, it contains both sp2 and sp1 atoms. So it will have different properties from the graphene. So it has linear structure, it's free of cis-trans isomer and planar polymeric network, uniform pore, and highly conjugated structures. The different connections can form different graphene. So we can see we can form a lot of graphene. So we can form alpha, beta, gamma, and if we have two carbon-carbon 3 bonds between the two benzene rings, we call it graphene. And this graphene is most widely studied, so I will most focus on this graphene. And this is also graphene's molecular structure. This is planar structure, and this is three-dimensional structure. We can see the host, universal pore, and this is the layer space. And graphene also has a lot of promising electronic properties. So it has high carrier mobility and also has natural bandgap. The bandgap is from 0.46 to 1.1 millivolt based on different calculations. And so graphene has shown a lot of promising applications in diverse fields. And I will focus on the catalysts for energy conversion. And we will give an introduction for the synthesis of graphene. And we can see the synthesized graphene is based on the coupling reaction, glass coupling reaction. And we first get the GMS protect the monomer, and we deprotect to get the monomer, and then we can get the graphene based from the copper substrate based on the coupling reaction. And this is some characterizations, the Raman spectra and XPS. And if we can tune the monomer, the concentration of the monomer and the ligand, we can control the morphology of the graphene. Here, we can control the morphology to synthesize the nanowall structure, and even we can control the nanotube. So, the above is the introduction of graphene. So next, I will introduce some my works about graphene. My first part is graphene and whole transfer layer for photoelectrocatalytic energy conversion. And in this work, we use quantum dots as a photosensor, and we know the quantum dots have a very good properties for photocatalytic, but its whole transfer rate is much larger. Its electron transfer rate is much larger than the whole transfer rate. So if we want to improve the overall efficiency, we must improve the rate of whole transfer rate. And we know we introduced before the graphene has a promising whole transfer rate mobility. So with this in mind, we want to assemble the quantum dots on the graphene to improve the whole transfer rate. Then we can get a good performance. So this work is designed like this. So first we synthesize the graphene on the copper foil, and then we assembled the quantum dots on the graphene, and this assembled and the photo cancelled, and we assembled the PEC cell for the photo PEC water splitting. And this is some morphology, and we can see the nanowall structure and this HRTM, and we can see this performance, and we can see it can produce 30 milliampere photocurrent and zero voltage, and the Faraday efficiency is about 90%, and it can keep stable and for 12 hours. So this is our first attempt. So it confirms the graphene can use and a good whole transfer layer for the PEC cell. And our next type is to fabricate a graphene photoanode, because before the last one is photo cancelled. So we wonder if we can use the graphene for the photoanode. The answer is yes. Here we select bismuth vanadate because it's a promising photoanode materials for oxygen evolution, but it has some advantages, but it also has some disadvantages, such as poor conductivity and its high electron-Hz recombination and poor water oxidation kinetics. So if we guess if we can combine graphene and bismuth vanadate, maybe we can overcome these disadvantages. But it's a problem. The graphene can only synthesize on this copper substrate. So if we want to synthesize on the graphene on the bismuth vanadate, it's impossible. So we must develop a method to synthesize the graphene on the bismuth vanadate. So we developed a method, we call it copper envelope method. Here we just use our copper to cover our substrate, and we put in our solution, and other conditions are the same for the synthesize of graphene. We can synthesize our graphene on arbitrary substrate, such as one-dimensional nanowire and two-dimensional planar plane and three-dimensional form. So after this method, we use this method to synthesize our graphene on this bismuth vanadate, and as it's expected, the synthesized graphene on this bismuth vanadate, the performance can improve largely. And we can see here is the bare bismuth vanadate, and here is the graphene coated bismuth vanadate. We can see the photocurrent improved largely, and this is photo stability. We can see the graphene coated bismuth vanadate keeps more stable than this bare bismuth vanadate, because this bare bismuth vanadate only usually occurred self-oxidation, but when we coated the graphene, the self-oxidation was inhibited, and the graphene can extract the holes to participate for the oxygen evolution instead of self-oxidation. And this is the whole injection rate. We can see the whole injection rate was improved largely after we coated the graphene. So these two work indicate our graphene can be used promising whole transfer materials for both photo-cancelled and photoanode. And the next work is the graphene as catalytic support for electrocatalytic energy conversion. And before the calculations, we can see the graphene can stabilize the nanoparticles or single atoms. We can see this is some calculations by others. So it has it's a promising catalytic support for metal nanoparticles and single atoms. So our first attempt for the electrocatalytic graphene is we synthesize the cobalt nanoparticles on this graphene form. So this is the copper form, and we synthesize the graphene on this copper form, and we use the in-situ reduction, and we can get cobalt nanoparticles on this form. And this form can be used directly for the electrocatalytic water oxidation. And this is some characterizations. We can see this cobalt nanoparticles is nearly 4 nanometers. And this is some Raman spectra and XPS. And this is the activity test. And from this activity test, we can see the self-supported electrode shows much better activities than others. And this is some your electroactivity test. And my third work, the third part is super hydrophilic graphene, both the electrocatalytic and photoelectrocatalytic energy conversion. Because, and we know for the gas-involved reaction, it only occurred on the triple phase boundary regions. It is gas and the solid electrode and the electrolyte. The reaction only occurred in these triple phase regions. But and we know the graphene is hydrophobic because it only contains carbons. So this hydrophobic is not good for the gas involution reactions because it always usually produces dead area and forming gas pocket. So we wonder if we can change the hydrophobic graphene to super hydrophilic graphene, maybe we can get improve the activity largely. So if we can engineering the interfacial microenvironment, it's very important to change the hydrophobic graphene to hydrophilic graphene. So with this in mind, here we use plasma treatment to treat this graphene, and after the oxygen plasma treat, we can change the hydrophobic graphene to super hydrophilic graphene. And the super hydrophilic graphene is because we introduced a lot of carboxyl groups and OH groups. So these groups are hydrophilic. So this graphene becomes super hydrophilic. And this is some structure. We can see the structure keep unchanged after plasma, but we can see the contact angle. This is very hydrophobic. But after treatment, we can see the contact angle becomes 0. So it becomes super hydrophilic. And this XPS, we can see it introduced a lot of carbon COH group. And the next, we assembled the LDH catalyst on this super hydrophilic graphene. And we first exfoliate this LDH and to get the single layer LDH, and then we assembled this LDH on this super hydrophilic graphene by electrocatalytic interactions. And this is some characterization after it's assembled. You can see it's assembled successfully, and we can see after it assembled the cobalt in the LDH after on the super hydrophilic graphene, the cobalt binding energy shifted higher, which means that there is much stronger interactions between the LDH and the super hydrophilic graphene. So it's better for the following OER reaction. And this is some test of the OER reaction and the RSV, and this is overpotential, Taffer plot, and EIS, and electroactivity area, and the stability. We can see the RDH assembled superhydrophilic graphene shows much enhanced activities compared to the hydrophobic one. And we also use DFT calculations to calculate the region for the enhanced activities. We can see after we introduce the COH group, we can see the COH group can attract the molecular, the water molecular closer, and it also can promote the distance between the catalyst and the water moleculars. That means it can promote the interfacial mass transfer, and also this COH group has stronger interaction with the catalyst. It also means it can also promote the electron transfer. So this superhydrophilic graphene can also both promote the electron transfer and the mass transfer in their interface. And then next, we also extended the superhydrophilic graphene on this PC cell. We still use the bismuth vanadate as the substrate, and we synthesize the graphene on the bismuth vanadate and use oxygen plasma to treat it. And we assembled the cobalt aluminum LDH, and this is the activity. We can see this black line is the superhydrophilic graphene coated bismuth vanadate, and assembled the LDH. You can see its activity is much higher than this superhydrophilic one. So that means the superhydrophilic graphene can not only used in the electrocatalytic, and it also can use for the PEC itself. And this is our invited review, and for this graphene materials for the gas involved reactions. So we produce some new ideas in this review. And this work is collaborative with Jordi and Xu. It's graphene for photocatalytic energy conversion. So as we know, as I before mentioned, the graphene has a natural bandgap, but its bandgap is very narrow. It's just from 0.46 to 1.1 eV. So it's very narrow. And we know if we want to fabricate the type 2 heterostructure in the very narrow bandgap is not good for the fabrication, because you should have the approximate line of the energy level. So if we can enlarge the bandgap graphene, maybe it's better for us to fabricate the type 2 heterostructure. So here we zero the doping the hydrogen atoms to enlarge the bandgap graphene, to enlarge its bandgap and to fabricate a type 2 heterostructure to improve the photocatalytic activities. And because, as we know, the graphene can be synthesized from bottom to up method, it can synthesize from the monomer. So if you can design different monomer, you can get a different graphene. So here we use this monomer because it has 3 hydrogen atoms. So these 3 hydrogen atoms can introduce the hydrogen atoms. So we use this bottom-up method. We synthesize the hydrogen substituted graphene. And this hydrogen substituted graphene, it has a bandgap of about 2.5 eV, much larger than the graphene, because graphene only have nearly 1 eV. And this is we hybridized with graphene with graphene and H-graphene with TiO2, and we synthesize this hybridized photocatalytic, and this is some characterizations. And this is our photocatalytic test. We can see our catalytic test. We can see this is for the content optimized, and the 5% is the optimized. And next we compared the H-graphene TiO2 and graphene TiO2. We can see the H-graphene TiO2 shows enhanced activity. This is in UV visible light, and this is in visible light. We can see the H-graphene shows very improved activities compared to the graphene. And this is for the pure water splitting into hydrogen, and these two parts we added the sacrificial agent. Next, DFT was used to calculate it. We can see here for the graphene. When it is combined with TiO2, we can see the energy level difference is very small. So it's not better for the charge transfer. But for H-graphene, we can see both different. This is a test for different physics of TiO2. We can see both of the physics. Both of these two physics, we can see the energy level difference. It is fit to the type 2 structure. So this type 2 structure is better for the charge transfer, the electron transfer here, and the hole transfer from here to here. So this is the structure is more better for the charge separation for the photocatalytic activities. This is some unpublished results, also collaborated with Xu and Jordi. And this is, and we know before I told you the graphene can only be synthesized on the copper substrate. And next we developed a method called the copper enveloper method to synthesize on the graphene on the arbitrary substrate. But if we want to use the graphene for the photocatalytic or other applications, we also use graphene powder directly. But others, previous method, it can only synthesize graphene on substrate. So we must develop a method to synthesize the graphene powder directly. And another limitation is when we synthesize the graphene, we must, because the HEB, this monomer, if we don't use the TMS protect HEB monomer, it is very sensitive. It's very sensitive to oxygen and water. So in our previous method, we first get this monomer, TMS protected HEB monomer, and then we deprotect to get the HEB and then synthesize the monomer. But here, we don't need to deprotect the TMS. We can start from the HEB TMS, and we just put this HEB TMS on this DMF, and we put copper chloride, and it can synthesize the graphene powder. We can see the yield nearly 100% yield. We also selected the different solvent and different catalytic, and we found that the chloride, boron, and iodine is better. So here we select the copper chloride, use the catalyst for the synthesizer of graphene directly. And another we found that this method can also get the copper oxide nanoparticles uniformly by this one port. So this copper oxide is a good catalytic for photocatalysts. So this is also another advantage of our method. So here I just show two figures about we can see this copper by this one pot method. We can see its activities is much better than other than other carbon materials, and graphene without copper oxidized. And we can see this method, we get the 0.5% copper oxide TiO2 is comparable to the even to the platinum TiO2. That means our method can not only get the graphene part with very high yield, it also can get the co-catalyst in this method. And this co-catalyst with the graphene has a very good activities even comparable to this platinum. And next, I will give an introduction about Mercury project. My Mercury project is for the site-specific heteroatom doped graphene for nitrogen reduction. And here we will design some heteroatoms doped graphene monomer, and we synthesize this monomer by different synthesize the graphene with different monomer. We can get different heteroatom doped graphenes. So that's all. This is some acknowledge. Thanks my supervisor Li Zhuwu, Jin Zhang, Gao Xin, and all my collaborators Gao Xin, Sophia, Naufa, Aihuan, Jordi, Xu, and the Int. And also thanks Mercury Fellowship. Thank you.
So now it will be time for questions. So first, if anyone in the audience want to ask, Jifu.
Thanks very much for your nice lecture. I have two small questions. One is that if we want to use the graphene to prepare the single atom catalyst, as you show in the lecture, and normally to fix the nectar in the substrate, the coordination structure, the coordination atom normally is nitrogen and oxygen. For the pure GDY, the element is carbon, but in my knowledge, the carbon normally is difficult to coordinate with the metal. So if we want to use the GDY to prepare the single atom catalyst, how is the coordination structure normally?
This structure I will show here, because now some papers about single atoms stabilized by graphene have reported. If you want to know, you can check. Because the structure is here. Because for the graphene, it's stabilized by this sp1 carbon atoms. Yeah, sp1 carbon. The sp2 is not cannot. We know it cannot, but the sp1 can stabilize the single atoms, and you can use electron reduction to synthesize the single atoms directly. And Professor Li Yuliang has published in Nature Communication, and in the Chem also has another paper for the single atoms. I can send to you if you want to learn.
And another small question. As you showed, the bandgap of the GDY is really narrow. Normally, it is cannot use for the photocatalyst directly because the bandgap is really narrow. So if you can we use the bandgap to change the layers of the GDY? For example, it is bulk material. For example, if it is bulk materials, the bandgap is really narrow. If we tilt to monolayer, whether the bandgap is larger or not?
Yeah. If we synthesize a single layer, it can improve. But for photocatalyst, we need a lot of samples, not a single layer. So it's impossible for photocatalyst. But if you want to synthesize some devices, use a single layer graphene, it's okay. But and the single layer, now we can synthesize 2 layers. Single layers maybe not achieved with very crystallization.
Thank you very much.
Continuing with this, how would you select the thickness of the graphene?
Thickness.
Yes. How can you do it?
In our previous work, we didn't consider the thickness because we, for our synthesize our nanowall structure, we can optimize the time to control the thickness, and we select the optimal time to get the thickness of the nanowall is nearly 1 millimeter. Yeah.
That's thick.
Yeah,
Really
that's thick. But if it's too thin, I think it can absorb less catalysis.
Okay.
Yeah.
And going to the super hydrophilic graphene, I had a question there.
Okay.
Because I've seen that you are using carboxyl groups in order to make the graphene more hydrophilic.
Yeah.
Is that right?
Yeah.
So comparing the hydrophobic and the super hydrophilic graphene with the carboxyl groups, what is the chemical difference there at the atomic or molecular level? So what is going on? Is that the water can be absorbed easier by this carboxyl, or?
Yeah, the water is easy to attracted by the carboxyl group. And here is the our DFT calculation. We introduce the carboxyl group, and this is the optimized the configuration. We can see the water can be attracted, and the water can be attracted, and the catalytic also can be attracted. This is LDH, and this is super hydrophilic, and this line is super hydrophilic. This line we can see it can not only attract the catalyst, it can also attract water, and it can also promote the distance, narrow the distance between them, because the catalyst, the reaction occurred catalyzed by this catalyst. So the water can be attracted on this catalytic is also good for the next OER.
Thank you. And I don't know if there are questions from the online audience, but then I have another question for you. Regarding to the attachment of metal or quantum dots to your graphene, that was at the beginning of your talk. You were showing that in order to activate the photocatalysis, you were using quantum dots of cadmium selenide. I remember it was. So yeah, exactly.
Yeah, it's quantum
here.
dots.
So if you, instead of quantum dots, were using single atoms, would it be possible to activate also the
no
photocatalysis? I don't think.
Photocatalysis,
Yes.
we didn't try because here the quantum dots, we assembled the quantum dots, we synthesize the mercapital pyridine. We use the four mercapital pyridine to functionalize these quantum dots, and the 4 capital pyridine has peptide interactions with the graphene. So we just need to put our graphene in this solution, and it can absorb by the peptide stacking.
Thank you very much.
Thank you.
So if there are no more questions and not more from the audience, so it's time to thank you for your talk.
Thank you.
And we have been super happy to know more about graphene for electrocatalysis and photoelectrocatalysis. Thank you very much.
Thank you.
Jian Li.